Hi everyone, this is Emrah Turgut. Today we will start chapter 21. And the chapter 21 is about circuits, bioelectricity, and DC instruments. So we will talk about series and parallel resistors, Kirchhoff's laws, and how we measure volt and current. These are some topics, more detailed list. In the circuits, we have two types of circuits. First one is series, and that's the one what you see on the left picture. Two bulbs are in series, which means that they have the same current passing on them. And the second version is the parallel. They don't have the same current, they share the current. The incoming current from the battery is split in two arms. They don't have the same current, but they have the same potential because these are the cables not without resistance. So they don't have a potential difference on them. Whatever potential you have here is the same potential. And at the end, they have the same potential as well because of this wire. So the series, the same current. For the parallel is the same potential. So how you find the equivalent resistance when you connect the resistors in series? So first, let's say you have the, you try to represent the R1, R2, and R3 by single resistor, which we called R equivalent. So let's find how you can find this in terms of R1, R2, and R3. So we'll have potential and you have R equivalent. You try to reduce the representation of this complex circuit into just simpler one. So the potential on V1 is going to be I1, IR1. V2 is IR2. So I can write in here. And the potential, let's say you can think as the battery increases the potential by V, and at each resistor you have a drop in potential V1, V2, and V3, which means that total V must be equal to V1 plus V2 plus V3. So if you write the V1 in terms of IR1, R2, and R3. Now you have common I. Okay, so you can simplify the math and you want to write this in terms of equivalent resistance. You have V equals I times R equivalent. So now you see that R equivalent is similar to R1, or in terms of math, R equivalent is R1, R2, and R3, a summation of three resistors. So R equivalent is going to be R1 plus R2 plus R3. So this is how you can find the equivalent resistance for the series circuit. So this explains the it's written here again. So this is how you can find equivalent resistance for the series circuit. Okay, what happens when you have them in parallel? So what happens, you will split the current in I1, I2, and I3. As I said, you will have the same potential on the circuit. So you try to represent in terms of equivalent resistance. So in this case, total I will be I1 plus I2 plus I3, right? And the potential on this, I1, R1, V1, I2, R2 is V2, I3, R3, V3. And V1, V2, and V3 are equal to V, the battery. And for the circuit, you can write I as a V divided by equivalent resistance, REQ, and I1 is V divided by R1, and I2 and I3 is represented by V divided by R2, potential divided by R3. And from you can simplify by dividing by potential this circuit, this equation. Then you will have R equivalent, 1 over R equivalent equals 1 over R1 plus 1 over R2 plus 1 over R3. So this is how you can find equivalent resistance in parallel circuit. So what happens when you have multiple resistors are in parallel and series? Then you can simplify one by one. First, you can start with the parallel circuit, the resistors. For example, here you have R2 and R3 are parallel. Then you can simplify first. We did this also in the capacitors. So R2 and R3 are parallel. And this can be simplified by 1 over 6 plus 1 over 6, 2 over 6. This is like R equivalent 1, let's say, like the first one, and 1 over 3, 3 ohm. So this combination, this circuit, is 3 ohm. And now R1, 6 ohm, is going to be series with the 3 ohm. R1, 6 ohm. And the equivalent resistance of R2 and R3 is 3 ohm. Now you have two series resistors, and you can sum them to find the total equivalent resistance. 6 plus 3 equals 9 ohm. So we found the total or the equivalent resistance of this whole circuit. And find the current in each resistor. So like the main current, or the current at the main arm, is going to be V divided by R equivalent, 18 volt divided by 9 ohm. We have 2 amp. So this 2 amp is gonna pass through R1. So R1 has I current of 2 amp, right? And now you have 2 amp and you must split them. This is kind of easy, straightforward, because the potential will be same on them, and they are the same. R2 and R3 are 6 ohms. So they will split their current equally, what happens is 1 amp is gonna go to R2 and 1 amp is gonna go to the R3. So total current must be conserved and the potential will be the same on R2 and R3. So 1 amp times R2 is 6 ohm, sorry. That will be 6 volt. And 6 volt. So another approach, like how you can approach this problem another way. So for example, for R1, you know it has 6 ohm and 2 amps. The potential on that, let's say V1 for the R1, right, is I times R1, 2 times 6 equals 12 volt. So if you think in terms of potential, you have a battery giving 18 volts, and the first resistor is going to consume the 12 volts, and the remaining 6 volt will go on this side. So this part is going to have 6 volt. So the R2 and R3 have the same potential, right? Then you can use 6 volt to find the current on the R2. It's 1 amp. I3 is going to be same way. 1 amp. I have one example. Let's assume you have infinite amount of resistors with 1 ohm resistance, but you need a 2.8 ohm resistance for a circuit. How would you connect them to reach total 2.8 ohm? So I will make this as a bonus problem. So whoever sent the first answer gets 2 extra credit point. Whoever submits a correct answer. So use email. You know my email address, emrah.turgut@okstate.edu. So this will make sure you guys listen the lectures and try to something by yourself. Actually, not just don't make one person. Let's make the first 5 people. First 5 people will get extra 2 credits points. So I guess you remember the capacitance we used. So in example, like you need to connect some of them parallel, some of them series, so you can get 2.8 ohm, but you must use only 1 ohm. You cannot use 2 ohm or 3 or any fraction. But you can use how many, as many as you want, 1 ohms. Okay, we now move on to terminal voltage. So which comes from, the term comes from the due to the batteries being not perfect. So which means that if you have a perfect battery without any internal resistance, the terminal voltage will be the voltage provided by the battery. But because they have some internal resistance, So when we talk about their actual potential, we need to calculate the terminal voltage. So let's say you have a battery, its EMF, electromotive force, is shown some voltage, let's say 1.5 or 3 volts. But because of internal resistance, when you pass a current, the useful voltage will be terminal EMF voltage minus the current times the internal resistance. So, I mean, this is a kind of more realistic picture. You have a battery, but it has an internal resistance you don't see. But when you pass a current, you must take into account, for example, the epsilon is the EMF force, electromotive force, and when the current passes, say I, then the potential difference between VAB will be epsilon minus I times R. So which means that in reality, batteries don't supply a constant voltage. The voltage depends on the current. So if you have a high current, the battery will supply less voltage. If you have a low current, very low current, the terminal voltage will be very similar to the EMF voltage or potential. So for example, we have it's a problem. As a flashlight battery ages, its EMF stays approximately constant, but its internal resistance increases. When the battery needs replacement, its EMF is still 1.5, but its internal resistance has increased to 1000 ohm. If battery is supplying 1 milliamp to the light bulb, what's the terminal voltage? So don't look at the figures. So this question is separate. So this is the first example we will solve. So if the resistance increases to 1000 ohm and it's supplying 1 milliamp, what's the terminal voltage? We will apply this VAB EMF minus I times R. We show the R usually as an internal resistance. So you have 1.5 volts EMF, and the current is 1 milliamp. In terms of amp, that's 1, and you have 1000 ohm. So this will be 1.5 minus 1 equals 0.5 volt. So terminal voltage is going to be 0.5 volt. Okay, this is the first example. In the second example, it's the left one. The battery above is added to open circuit. What are the readings for the voltmeter and ammeter? So you have this circuit, it's open. So which means it's not complete. Thus, the current must be 0. So if the current is 0, the terminal voltage will be equal to the EMF voltage, right? Then this will be 12 volt. Now you have added a resistor, which is 4 ohm. And now you complete the circuit and the current is gonna flow. And it says what's the terminal voltage. Okay, let's first find the current. Now this small r and capital R are in series. they have the same current passing through them. So then you can just add them. Equivalent R is going to be 4 plus 2, 6 ohm. Then the current will be 12 volt divided by 6 ohm, 2 amp. Then the terminal voltage, the epsilon, the battery's EMF minus I times internal resistance, small r. 12 volt minus 2 amp times 2 ohm. It's the internal resistance. 2 ohm. So you have 12 volt minus 4 volts, 8 volt. So the voltmeter is going to show this 8 volt, which is VAB, and the current is 2 amp. So that's all for today. Next lecture, we will talk about Kirchhoff's laws, and see you later.